Hi, welcome back. So in this video lesson, we'll elaborate on the concept called the model complexity. We mentioned model complexity to be the heart of machine learning. So in the previous video, we took a case study around Fukushima nuclear power plant disaster and narrated how an overfitted model can lead to such a disaster. So in this video, we'll continue on the discussion and define the terms underfitting and overfitting in as simple terms as possible. So let's get going with our uh, learning. So as we mentioned, model complexity is one of the most important concepts for practical machine learning. So as machine learning engineers, as machine learning designers and project managers, we must grasp this concept as clearly as possible so that we'll be able to deliver these projects more successfully. So with that in mind, let us understand this model complexity concept clearly. So before we again talk about model complexity, we have been talking about the machine learning models and defined machine learning earlier on in our videos. So let us recap on the definition of our machine learning. That is the practice of teaching computers how to learn patterns from data, often for making decisions or predictions. So in any machine learning model building exercise, we provide a data file as an input to our computer, and we let the computer to decide and understand the the underlying relationships that exist in data, so that an unseen new data is provided to that model. Then our model should be able to make a prediction about the new unseen data. Or if there is no labeled data, that's what we refer to as unsupervised learning, then actually look at the data and group the data in a way that an automated data analysis can be performed on data for some useful purposes. So any machine learning exercise, what do we do as engineers? We build models. So what is a model? Model is a simplified representation of the real world that still accurately captures a desired relationship. That is how we have defined a model. So what is this simplified representation of what the relationship that exists in any data set between the input features and the target variable? So a good model should accurately capture the desired relationship in a as simplified representation as possible. So in our Fukushima nuclear power plant case, what happened? Though there is a relation that exists between the input features and the predicted variable, that is a linear relationship by some of the previous scientists, they told about a rule, but still the machine learning model captured it in a much more complex manner than a simple linear model. That is where it went wrong. So it's very important that we build models in such a way that they accurately capture a desired relationship. If they complicate that, then it's not a good model. At the same time, if they are not even capturing the desired relationship that exists between the input features and target variable, then also we are not building a right model. So that is the point that we will try to understand. And just having a recap of what we talked about models and machine learning sometime back, we talked about an analogy of the candle and the stove top and the curious kid. So what happened in that analogy? Curious kid stuck her finger over the candle and then learnt a lesson that red and bright means painful, and that we called it as a model, mental model she created. And it's a very simplified representation. It did not have any complexities. The kid is a very small kid. She doesn't know thermodynamics, she doesn't know combustion, she doesn't know nerve endings and neuroscience. Still, based on the experience, she got a simplified representation of what does red and bright mean, and that she has used to protect herself in the future. So for a model to be useful, it must still accurately capture a useful relationship. It should not overcomplicate that, but it should minimum capture it accurately. And machine learning builds those models by learning patterns from data. That's what we have been talking. So model is an output of the machine learning process. So as machine learning designers, machine learning engineers, when we do machine learning projects, the output that we provide is build a model which is good, meaning it is not a overfit to the problem that we are solving. At the same time, it is not an underfit to the problem that we are solving. So we will be defining those terms called overfitting and underfitting in this video. So before we get there, let us get into a little bit of mathematics here, because when we talk about the relationships between an input and output, or input features and the target variable, it can be expressed a lot of times in mathematics, especially when we build computer models. It's purely based on mathematics. So let us define this in a mathematical way. So another way to understand models is to think of them as mapping functions between input features and target variables. So any data is there where there are a set of input features and there is an output that is we are trying to understand, then there is a mathematical equation, and that can be always defined as y hat equal to function of x. So what is x here? X is the input feature. So, and y hat is the predicted target variable, and the relation between the y hat and the input feature is a function of x that can be represented in any mathematical function. It can be a linear function, it can be a quadratic function, it can be a polynomial function, or it can be a sinusoidal function, anything. So understanding the relationship between the input features and target variable, there may be some mathematical equation that will be useful to represent that relationship. So that is what we are really doing as we build models. So therefore, the purpose of machine learning is to estimate that mapping function based on the data set that we have. So basically, we don't know what is the real relationship. We don't know accurate mathematical function. So a model's role is to, or machine learning's role, the purpose is to estimate that. Many ways the data can be explained, the relationship between the input features and the target variable can be explained, but finding that exact mathematical function that will help us to predict the target variable for an unknown input feature, if it can be as accurate possible using a particular mathematical function, and that mathematical function that we are really trying to estimate using our machine learning process. So keep that in mind as we talk about it. So as you build models as part of machine learning projects, key questions you have to ask. So first one is, which type of algorithm should I use to build the model? So there are many algorithms representing many mathematical relationships. So for example, in our Fukushima nuclear power plant disaster, so the Gutenberg-Richter rule was telling that the relationship between the input features and the target variable follows a little bit of linear model, but for some reason the model has taken a little bit curved route, and that's where actually they failed to predict accurately. So we have to ask this very important question: which type of algorithm should I use to build the model? Then which algorithm settings should I tune? Again, we'll talk about all these things later, but algorithms again have to be tuned for specific settings. If it is a polynomial function, what are the coefficients? How do I tune them? And so that I get a good representation of the relationship as good as possible. And also we have to ask, how many features should I include? I have in my data a lot of features, but should I use all of them, or which of them, by using which of them I'll do better benefit? So these are the questions we have to ask, and to answer all these questions we talk about this concept called model complexity. So model complexity is model's inherent flexibility to represent complex relationships between input features and target variables. If it is too flexible and it tries to capture everything in the data and try to map to a function between the input features and the target variable that includes the signal as well as the noise, and it is too flexible, then we are building a very over complicated model. And if you are building a model which doesn't even bother to capture some relationship that exists between the input features and target variable, then also it is not a good model. That is a underfitted model. So model complexity, by understanding that, as designers we have to do a very good balancing act between should I make it very complex kind of model, or should I make it a very easy kind of model? So we have to always take the middle path. So we are defining that aspect as we build the models, and model complexity is an important thing to understand. So we defined model complexity earlier using signal versus noise analogy. So again, let's recap. So signal is the true underlying relationship between input features and target variables. Always there is a true relationship that exists. That is what actually we have to really capture. And noise is what? Noise is randomness in your data that you can't control and you don't know. But every data set will have some inherent noise that we have to be aware of that. So the practical challenge in real world machine learning problems is actually dealing with noise. How do I avoid that noise? How do I not really read that and unnecessarily make a not so great predictive model? So therefore, one way to judge models is by their ability to separate the signal from that noise. That is the very important balancing act we have to do. And let us define overfitting. Same things can be defined using this overfitting and underfitting terminology. So how does this relate to model complexity? So in applied machine learning, model complexity manifests as overfitting or underfitting. So overfitting, it occurs when the model learns the noise instead of the signal. If you do that, then actually you are overfitting the model. So what happened in the Fukushima case? There it has somehow the linear model at the time of 8.3 kind of Richter scale measurement, it went a curved kind of route, and that is how the model went wrong there. So this tends to happen when the model is too complex. So we should not try to build too complex models. So it has to only capture the signal. That is very important. So how do we define underfitting? So underfitting happens when actually the model is not flexible enough to learn the signal. So this tends to happen when the model is too simple. So it is not even capturing some basic underlying relationship that exists between the input variables and the predicted variable. So then actually we are underfitting. So the same thing in machine learning terminology, we use some lens through which we learn this, that is called bias variance trade-off. So we will talk about bias variance trade-off in another lesson, but for now keep in your mind model complexity when we are defining. That is a very important term, and we have to understand that what is overfitting of a model and what is underfitting of a model, and we have to be aware that we will not go either direction. We are doing a right kind of balancing act. So before we conclude this session, let us do a quick knowledge check. So think along with me and tell the statements below whether they are a true or false statements. So the first statement, underfitting, is when we train a predictive model that hugs the training data too closely. That is what happened in our Fukushima case study. So underfitting is when we train a predictive model that hugs, means that is very close to the training data. That is why it was misled and it took a curved course. So do you agree or not? Yes, it is a false statement. Underfitting is when we train a predictive model that hugs the training data too closely. Is not correct. It is overfitting. So if you underfit, means you are not even capturing the relationship. So the second point is you have state-of-the-art algorithms, the fastest computers, and the most recent GPUs. But if your model overfits or underfits to the training data, its predictive power are going to be terrible, no matter how much money or technology you throw at it. Hope you understood the statement. No matter what is the technology that you are using, but if your model either underfits or overfits, then it is a terrible activity. Agreed or not? Yes, you are right. So underfitting or overfitting, both of them are not good for building good models. A rightly fit model, that is what our intention to build. So when a model ignores important features of our data and is not complex enough to capture important features, that is called underfitting. Agreed or not? Yes, you are right. That is the definition of underfitting. So hope you have understood this concept called model complexity. And what we will do in the next lessons is that we will create a synthetic data and experiment with many models, both underfit models and overfit models, and create a good intuition to understand this concept, because this is a very important concept. So stay tuned for those videos. So till then, learn and have fun.